So today we are going to discuss the topic of modeling distributions or designing graphic models on data in the form of sets, how to select multiple subsets or combinations of subsets of objects or entities, for predictions or for recommendations. Today, I'm very happy to have one more guest lecturer, Dr. Pengtao Xie, who was a former student in my group, and he graduated last year, and then he's now an assistant professor of computer science in University of California at San Diego. So he graciously agreed to help delivering this lecture because he has been working on this topic for a long time and also had a lot of very successful applications, especially in healthcare domain, where you need to recommend or report sets of findings or sets of treatment recommendations and so forth. So again, as usual, you are expect to unmute yourself while listening, but you are welcome to pose questions by raising your hands, and either the TAs will be chatting with you, or Pengtao himself will be taking your question directly and answer your questions online. Otherwise, when you are listening, please do unmute yourself to avoid the interference of the noise. So with that, I want to hand it to Professor Xie, who is going to kickstart his lecture. Thank you, Pengtao.
Hello, can you hear me?
Yes, I can hear you. Thank you.
Thanks, Eric, for the introduction. Hello, everyone. I'm very happy to give this guest lecture. So previously in this class, most of the distributions you have learned are about over vectors. In last lecture, you learned a distribution over functions, which is a Gaussian process. In this one, we are going to talk about the distributions over a new type of objects, which is sets. In particular, we are going to discuss the determinantal point process, which is a distribution over the sets. In this lecture, we are going to cover the topic of subset selection. In particular, for determinantal point process, we are going to talk about the basics of this distribution, how to draw samples from this distribution, how to find the mode of this distribution, and how to learn the weight parameters. Then we are going to extend to conditional determinantal point process and the K DPP. So one nice thing about the DPP is that it has inductive bias over diversity. So we are going to briefly introduce the diversity promoting learning as well. Okay, let's get started. Subset selection, it is a problem that widely exists in machine learning applications. The setting is given a set of K items. We want to select a subset from them. There are many applications that are under this umbrella of subset selection. For instance, in the extractive document summarization, the goal is given a document containing K sentences. We want to select a subset of the sentences to summarize this document. And in feature selection, given a set of features, we want to select a subset of features to either speed up the computation or making the analysis of the model easier. In product recommendation, we are given a set of products, and our goal is to select a subset of them to recommend to the users. When we are doing the subset selection, oftentimes we want to pursue diversity. That means we want to prefer the selected items to be mutually dissimilar from each other, in other words, diverse. Again, in the aforementioned applications, we do have a need to achieve diversity. For instance, in the extractive document summarization, we want to select the sentences that are representative about this document and non-redundant, right? We don't want to select the sentences that are talking about the similar things to summarize the document. And also in feature selection, we want the selected features to be non-redundant, right? It makes no sense to select two features that are highly similar to each other. And for product recommendation, we want to recommend diverse products to the user rather than recommend products that are from the same category to the users. In this lecture, we are going to mainly focus on determinantal point process. It serves two purposes. One is it nicely defines a distribution over the subsets, so we can build probabilistic models for subset selection. And also this DPP naturally favors diversity. So that means it will have larger probability mass over the subsets, whereas items are more diverse. So DPP, it is a distribution over subsets, and it favors diverse subsets. Given a set of k items, AI, A1 to AK, where AI is the feature representation of the item I. For instance, in document summarization, AI could be the embedding of the sentence. In feature selection, AI can be the distribution of this feature over the data examples. And in product recommendation, AI could be some embeddings or extracted features of the products. So how can we define a DPP over the subsets? The procedure is as follows. We first calculate a k by k gram matrix L, where Lij is the inner product between item I and item J. The inner product, as you know, measures the correlation or similarity between the two items, right? So we calculate this similarity between every pair of items in this set and get this k by k matrix. Then given a subset Y, which is a subset of the calligraphic Y, how can we define this DPP? It is given in this equation. The probability over this subset is the ratio between these two quantities. On the nominator, it's the determinant of a submatrix of L. The submatrix, in the submatrix, the rows and columns are indexed by the elements in the subset Y. I'm going to show you an example later on. And on the denominator, it's the determinant of the gram matrix L plus identity matrix. Let's see an example. So in this full set, we have 4 items, 1, 2, 3, 4. We first calculate the gram matrix, which is a 4 by 4 matrix that measures the similarity or inner product between every pair of items. Now we want to define a distribution, define a probability over the subset Y, which contains 2 elements, 2 and 3. What we do is we pick up the submatrix of L, where the rows and columns are indexed by the elements in the subset. So it includes L22, 23, 32, and 33. Then we can calculate the determinant, right, over the submatrix, which is on the nominator. And on the denominator, it would be the determinant of the full matrix L plus identity matrix. Yeah, this would be the definition of the determinantal point process. Very simple and neat. Now let's see why the determinantal point process has inductive bias over diversity. By diversity, it means that so the DPP will have higher probability mass on a subset where the items are more diverse. Why DPP has this property? Here is an illustration from the geometry perspective. It turns out that the determinant of this submatrix is actually the volume of the parallelepiped formed by the vectors in the subset indexed by y. So suppose in the subset y, we have two elements, and these two vectors are the feature representations of these two elements. Then the determinant of this submatrix we show here is actually the volume of this parallelepiped formed by these two vectors. So now we can see that the volume depends on two things. One is the magnitude of these two vectors, right? So if we enlarge this vector, the magnitude of these two vectors, the volume will increase. The other thing is the more dissimilar the two vectors are, the larger the volume is. You can see a comparison here, right? In this case, the two vectors have the same magnitude. In this parallelepiped, the two vectors are similar to each other. They have a larger inner product and a smaller angle. And in this case, the two vectors are more dissimilar to each other. They have a larger angle and a smaller inner product. As you can see, when these two vectors are more dissimilar, the volume is larger, right? And since the probability is proportional to the volume, then we can conclude that the more dissimilar the vectors, the items are, the larger the probability is. So DPP has this inductive bias over diverse subsets of items. In graphical models, one important thing is the partition function, right? Which ensures this probability integrates to 1 and ensure it is a proper probability. And in DPP, the partition function is basically this term, right? That ensures the integration of the denominator over all the subsets equal to this denominator. In most of the graphical, so if we want to define a graphical model, say conditional random field over the subsets, oftentimes the difficulty is the partition function is going to be very complicated and difficult to compute. One nice thing about DPP is the partition function has a closed form expression, and the closed form is very simple and neat, and you can do efficient computations over it in polynomial time rather than exponential time. Now let's prove why this determinant of L plus I is the partition function of the DPP distribution. So by definition, partition function means this partition function equals to the summation over all the subsets that ensures this probability integrates to 1. So to prove that this is the partition function, let's first prove a theorem. So in this theorem, it says that given any subset A from this universal set calligraphic Y, if we do a summation over the subset Y, which is a superset of A and a subset of the calligraphic Y, the term we are doing the summation over is the determinant of the submatrix indexed by the elements in Y. And this summation equals to the determinant of this matrix L, the full gram matrix, plus this matrix I A bar. The I A bar matrix is defined in the following way. First, it is a diagonal matrix, where on the diagonal, the position of the ones correspond to the elements of the complementary set of A, and this matrix have real zeros elsewhere. Let's see an example. So we have a universal set of Y, and say this arbitrary set A is 2 and 4. Then the complementary set of A bar would be 1 and 3, right? And so in this matrix I A bar, according to the definition, 1 and 3 on the diagonal will have 1s, and all the other entries are 0. We prove this theorem by induction. So for the base case, let's assume that A is the universal set, categorical Y. Then the proof is trivial when A is the universal set, right? Then this Y is basically a universal set as well. And we only have one element here, which is the determinant of the full gram matrix. And when A is the universal set, A bar would be empty set, and I A bar would be a 0 matrix. So on both sides, we have the determinant of this gram matrix L. So this theorem holds. Now let's go to the induction step. So in the induction step, the assumption is that the theorem holds whenever A bar has cardinality less than K. So based on this inductive assumption, we are going to prove the following case. Let's say we have a set A, so that the cardinality of the complementary set is K. So you can see that in the inductive assumption, we assume that it is less than K. Now we want to prove the case that the cardinality of this A bar is K. We have an item I, which is an element of the universal set, and this element I belongs to the complementary set of A. Now let's start this proof. We first do a blockwise partition over the universal set. One partition is this single element I, and the other partition would be all the other elements. And based on this partition, we can write this matrix L plus I A bar into this form. Let's first see L, right? According to the partition, the first, so we have 4 blocks, right? On the diagonal block, corresponding to I would simply be LRI, and on the rest of the diagonal would be simply L Y excluding I. Then off diagonal, the 2 blocks is simple as well. So here, I bar denotes basically is Y minus I, all the elements in the universal set except I. So naturally, based on this partition, we can write L into this form. There are 4 sub-matrices. Then let's take a look at this matrix I A bar. So according to the definition of I A bar, it is a diagonal matrix where ones in the diagonal positions corresponding to the elements of A bar. Since I is an element of A bar, so the corresponding diagonal entry would be 1, right? And the off diagonal entries are all 0. And then for rest of the diagonal entries, according to the definition, all the all the elements in A bar would be 1. And I is our element in A bar, but we already put it here. So the rest of the elements in this set, y minus A minus I, would be all be 1. Right? This is from the definition of I A bar. Then we sum these two matrices together and get this form. For the next step, we utilize the linearity of the determinant to get this equation. Linearity of determinant means the following. So we have a matrix where the column vectors are R1, R2 up to Ri minus 1. Then we have a column vector here, which is a linear combination of two vectors. So we first multiply this vector Ri with a scalar s, then plus another vector Ri prime. Then we have the rest of the column vectors Ri plus 1 up to Rn. So the multilinearity means if you have a matrix where one of the column vector is a linear combination of two vectors, we can write them apart. Say for the scalar multiply this vector, we can write it into scalar multiply the determinant of the matrix formed by this column vector Ri, then plus the determinant of the matrix formed by another vector I prime. Right? You can clearly see that there is a linear structure here, right? So given this linear combination, you can write it down, break it into a linear combination of the determinants. So based on this property, we can write this equation here as a linear combination of two determinants. So here we will do the breaking over this vector here. So it is Lii 0 plus 1 0, right? Li here is, so this vector Li plus 1, Li I bar can be written as Lii 0 plus Lii I bar plus 1 0, right? So this vector here can be written as the summation of these two vectors. And for the other row vector here, we keep it. So according to the multilinearity, right, we can write the determinant of this equation of this matrix as the summation of these two matrices. Then for the next step, we are going to write each of these two determinants into these two forms. So for this one, it is simple, right? You just do it over using the definition of determinant. So these two terms cancels, then we get determinant of this matrix. And for this one, so we know that L can, according to the partition, Y union I union universal set excluding I, we can write this matrix L in this form, right? Getting these block partitions. And for this matrix here, I A union I bar, according to the definition of I A bar, we can write it into this form, right? For this element I, since it is part of the this matrix AI, then it cannot be in this set, right? So the corresponding element is 0. And then for this set, y excluding a excluding I, since they all belong to this complementary set, then there are, so the corresponding diagonals would all be 1. So we can put these two terms together, right? We exactly get this this matrix. So the determinant of this matrix can be written in this form. Now, starting from equation 2.10, we are going to utilize the inductive hypothesis and get the following equations. Let's recall the inductive hypothesis is that so if A bar has cardinality less than K, then this equation holds, right? Now let's check the cardinality of this A union I set. So the cardinality of A bar, according to the induction assumption, it is K, right? Then the cardinality of A would be capital K minus small k, where capital K is the size, is the cardinality of the universal set. Then we add one more element I into this set. Recall that this element I does not belong to A because I belongs to A bar. Then the cardinality of this set would be capital K minus small k plus 1. Then the cardinality of the complementary set is K minus 1, right? Then according to the inductive hypothesis, this set satisfies this condition, has cardinality less than K. So we can apply this equation here. And then this term can be written as this term, right? You just replace A with A union I, and then directly get this new quantity according to this equation. And similarly for this one, it naturally, right? If you compare this equation and this equation here, you can easily get a form like this. Now we have two cases that the subset Y either contains I or do not contain I. We can combine them together and get this quantity. Then we basically prove this induction step, right? And the induction proof procedure completes. Now, given this proved theorem 2.1, we can easily show that this partition function holds, right? We simply let this set A to be an empty set, then we get this equation here. Okay, all right. So this is the proof of the partition function. Now let's see a few extensions of the determinantal point process. The first extension is to kernelize DPP. In the original definition, we have this gram matrix where the elements are the inner product. Right? When you see inner product, naturally you can connect it to kernel. Kernel is basically we first transform these two vectors through some nonlinear transformation and get two representations in the nonlinear space. Then we take the inner product in that nonlinear space. And this inner product can be implicitly calculated by a kernel. So we replace this inner product in the gram matrix with a kernel function and get a kernelized DPP. The definition is the same, except that the gram matrix now is calculated as a kernel matrix instead of the original inner products. And we can also combine DPP with deep learning. it's also very simple to do. We just, given these two vectors, we just use a deep neural network to transform, to embed them into a nonlinear space, then takes the linear product over the neural network latent space. This is a special type of kernel, which is called the deep kernel. But now the difference is you have, this kernel is parameterized by the weight vectors in the neural networks. So you can do the learning of these neural network weights. And for the definition, it remains the same, except that in the gram matrix, the inner products is calculated over the latent embeddings achieved, obtained by deep neural networks. For the next step, let's talk about algorithm, how to draw samples from DPP. DPP is a distribution, right? We should be able to draw samples which are subsets from this distribution. The sampling procedure is as follows. So given this matrix L, which either can be a gram matrix or kernel matrix or deep kernel matrix, we first do a eigen decomposition of this matrix, and we get the eigenvalues and the eigenvectors. So the sampling procedure has two parts. In the first part, we first sample a subset of items and put them into this set J. So initially it is empty. Then for each of the items in the set, now we have a new notation, capital N, which denotes the cardinality of the universal set, the number of all items. And for each item, we sample it with probability lambda n over lambda n plus 1, where lambda n is the eigenvalue of the corresponding to the nth item, right? You uniformly draw a uniform random number and compare with this probability. And if it is larger than the probability, smaller than this probability, we put this element into this set J. And do this for all the items. And in the end, we get a subset of items, right, according to this probability. And this subset of items, okay, now we get a subset. The next thing we do is we take the eigenvectors corresponding to the subsets. So for each element in this subset, we take the corresponding eigenvector and put them into another set way, which contains a subset of eigenvectors. Then in the next step, we are going to, in the next part of the sampling algorithm, we are going to sample another set of items. The procedure is as follows. While the cardinality of this set way is greater than 0, from this universal set, we select item I with this probability. So EI is basically an orthonormal basis, where the ith element is 1 and all other elements are 0. We take the EI, takes the inner product between EI with every eigenvector in V, and squares the inner products, sum them together, and normalize with the cardinality of V. Essentially, this is calculating, let's first see this matrix V. So here, this matrix V contains all the eigenvectors that are indexed by these sets. So the number of column vectors is the cardinality of this set J. Give me a second. I saw there might be a question. Oh, there was a question. Why is eigenvalues are always non-negative for any kernel? Is this true? So remember that this matrix L is gram matrix or kernel matrix. So it is it is always positive semi-definite, right? So that means the eigenvalues will always be non-zero, and it is almost sure that this matrix is positive definite unless the items are linear correlated. And here, for simplicity, we basically assume that these vectors are not linearly correlated, and then this matrix L would be positive definite, and all the eigenvalues would be strictly positive. Okay, all right. Let's see this matrix way, right? The number of row vectors, column vectors is the cardinality of J, and the dimension of each vector would be the number of elements. Sorry, I should put n here instead of k. So this equation here is basically calculates the squared L2 norm of a row vector corresponding to the element I. And according to the property of eigenvectors, each column, the norm of each column vector is 1. We have so if you sum all of them together, the summation would be the cardinality of V. So that's why this probability is a probability, right? It sums over to 1. Okay, all right. So according to this probability, we select item I and put it into this set Y. And after we select item, we will do operation to transform this eigenvectors matrix. We are going to find out the subspace of V, where the subspace is orthogonal to EI. And after we get this subspace, we are going to find out the orthonormal basis of this subspace. And this orthonormal basis would be this matrix here. Then we replace the matrix V with this new matrix. John was asking, answer your question. Yeah, I think yeah, the student acknowledged. Yeah, okay, all right. Then we repeat this procedure until there is no elements in V, and in the end we select a subset of items. What is EI? EI is so basically say let's say I is 3, then EI would be a vector. On the third position, the element is 1, and in other positions, the element is a 0. Okay, and so if you want to check why this sampling algorithm ensure that the samples drawn according to this algorithms are from DPP, so in the end of this lecture, there is a reference slide, and you can take a look. Due to the constraint of time, we are not going to prove this in this class. But intuitively, why this sampling method ensures diversity? The major intuition comes from this part. So whenever we sample an item, we are going to find out a subspace that is orthogonal to the sampled item. Orthogonal, right, induces very large diversity. So basically, make sure that the inner product of the rest of the items is different from the already sampled one. That's where the diversity comes from. Now, given a distribution, in addition to drawing samples from this distribution, another thing we want to do is to find out the mode of this distribution. For instance, suppose we define in the extractive summarization task, suppose we define a probability over the sentences. We want to see which subset of sentences gives the largest probability, and we are going to use that subset as summarization, right? So to achieve that goal, we need to find out the mode of the DPP. A mode of a distribution is basically the configuration. Is basically the subset that yields the largest DPP probability. Here we don't need to care about the denominator and only care about the numerator. And typically for the ease of computation, we put a log over the determinant of this submatrix, and the log does not change the monolicity of the distribution of the quantities. So finding the mode essentially is to find out a subset of Y that yields the largest quantity, the log of the determinant of the submatrix indexed by Y. Finding out the exact solution is NP hard, right? If you think about it, how many choices we have for Y, it is exponential, right? It's 2 to the power of the cardinality of Y. So people have developed approximate algorithms to find out the mode. Here we introduce one particular method, which is relatively easy to implement. The idea is simple. We first do a continuous relaxation of the item selection variables. So in the hard selection, it's either 1 or 0, right? 1 means item is selected, and 0 means it's not selected. So in the continuous relaxation, we relax this 0, 1 selection into basically a probability between 0 and 1. And the larger this probability is, it means that the more likely that this item is going to be selected. After we do the continuous selection, we can do continuous relaxation of the item selection variables. We can do a continuous relaxation of this objective we want to maximize. And the relaxation is given in this equation here. Here, Y is a vector. The length of Y is the number of elements in the universal set. And for a particular element in Y, say Yi, it is a probability indicates how likely this item I is going to be selected. So Y is a continuous vector, and each element is in this interval 0 to 1. So here, this is the diagonal matrix where the elements on the diagonal are the elements in Y. L is this gram or kernel matrix, and I is identity matrix. This is the log of the determinant of this matrix. This is a continuous function defined with respect to Y, right? We can do the whatever method we want to use to do the optimization and find out the Y star that maximizes this function Fy. After we get Y star, we can do a rounding over the elements in Y star and get them back to 0 and 1. Say if the element in Y is less than 0.5, we round it to 0. Otherwise, it is rounded to 1. After you get this rounded 0 and 1 variables, we basically do a selection according to this these variables, right? If the variable is 1, we select the corresponding item and do not select otherwise. So we talked about how to draw samples and how to find out the mode. Assume that we are given a DPP. Then the next question is, in DPP, we have the weight parameters, right? How can we learn these weight parameters. For instance, if the DPP, the L matrix is calculated using a kernel, in the kernel, we have the hyperparameters of the kernel, right? Like in the RBF kernel, we have the scaling factor. In metric Mahalanobis metric-based kernel, we have this Mahalanobis matrix. Those are the parameters we want to learn. And in the case of deep DPP, remember that the kernel is calculated using neural networks, right? In neural networks, we have weights. Those things are learnable. How can we learn these weight parameters? So we assume that to learn these parameters, we assume that the data we are given are universal set together with the ground truth selected subsets. For instance, in the training data of extractive summarization, we have for each document we have the all the sentences which are observed, and we also have the ground truth summarization, which is a subset of sentences that are labeled by the human annotators. Then, given the universal set and the subset, right, we can define the probability over the subset using the DPP distribution. So we have n training examples, say n documents. For each document, we have the all the sentences in that document and the ground truth selected ones. Then we can plug in the feature vectors of the selected ones into the DPP distribution and get this DPP probability. Then we right. So here we define a maximum log likelihood objective function. Multiply all the probability over different training examples together. Take a log. Then we get this objective function. Then we can do the gradient descent or other method to optimize this function with respect to the hyperparameters or weight parameters in the kernel or in the neural network. So far, we talked about DPP, which is given a universal set, we select a subset. And the selection totally depends on the relationship between the items in this universal set. Specifically, we want to select diverse items. But in many other applications, the selection of subset not only depends on the relationships between the items in the universal set, but also depends on the relationship between items with some external information. For instance, in personalized product recommendation, we have a user and we have some information about this user and a set of products. When we are doing the selection of the products, we not only want to select diverse products, but also the products that are highly relevant to the interest of the user, right? For each product, we can measure its correlation or relevance to the information of this user and take that into account when we are doing the selection. And in this scenario, if we want to define a DPP, that would be called conditional DPP, conditional on the external information, such as the profile of the user. And how do we do that? It's simple. When we are calculating the kernel matrix, we basically calculate a conditional kernel instead of just a regular kernel. The conditional kernel means when we are calculating the similarity between two items, we not only consider the similarity between these two items, but also their relationship or relevance to this variable that is conditional on. For example, in this product recommendation application, X would be a user and we have two products, AI and AJ. On the information of these two products, we can calculate a similarity score. And meanwhile, we can calculate the similarity between the information of a product and the profile information of the user, and multiply them together. Here gives an example of this conditional kernel. So S is a kernel function that measures the similarity of two products. And G is another function that measures the similarity between a product and the user. And we multiply them together. And it is easy to say that this is a valid kernel as well. After we get this conditional kernel, we apply it to every pair of products and get this conditional kernel matrix. And then we, based on this conditional kernel matrix, then we can define this conditional DPP, the probability over subset conditional on the external information X. And here, just a note that when we are calculating the kernel matrix, always takes this external information X into account through this conditional kernel. So here we have a case study, which we utilize the deep determinantal point process for multi-label classification. And the DPP here is a conditional DPP. Multi-label classification is a problem that we are given an input, for instance, an image. And we have a set of candidate labels, for instance, the 1,000 class labels in ImageNet. And in multi-label classification, we want to select a subset of labels and annotate this image using this subset. For example, given a picture that is taken inside the house, we would have sofa, right? Have desks, have lamps, and in this image, because there are many different objects, so we are going to assign a subset of labels to this image. And this is called multi-label classification. How can we use conditional DPP to build a distribution over the label subset? As we just discussed, we should first define a deep conditional kernel. The kernel is defined in the following way. Let's say we are given two labels, sky and ocean, and image X. We can get some word embeddings of these two labels and use this network to get an embedding of this image. Then we use another network which takes the embedding of the label and the embedding of the image as input and calculate a score that measures the similarity or relevance between this label and this image. Similarly, we do it for another label and the image. Then between these two labels, we want to calculate how correlated or similar they are, which is done by feeding their representations into another neural network and get a kernel function. Then we multiply these three scores together and get this conditional kernel. Then we, based on this conditional kernel, we apply it to every pair of labels and get this conditional kernel matrix. And then we define a distribution over a subset of labels S conditional on the image X. So this is the conditional DPP defined over label subset. And in the conditional kernel, we have these weight parameters of the neural networks. We want to learn them. So in the training data, we have the ground truth training pairs, where X is our image, S is a subset of labels that are annotated to this image, and the S and X are both observed. Then we can put S and X into this probability, right? And multiply the probability of all the training examples together, and then do the maximum likelihood estimation to learn the weight parameters. Here I want to talk about something that exploits the property of DPP for incorporating external prior knowledge. So when we are doing the label assignment, we oftentimes we have some prior knowledge regarding certain labels are very likely to be assigned to an image simultaneously. For instance, sky and cloud are very likely to be simultaneously assigned to an image, right? And those binary relations are called masked links, which means that if there is a masked link between label I and label J, then it is likely that I and J are going to be simultaneously assigned to this image. On the other hand, we have these cannot links. Let's say maybe a cloud and a dog is not likely to be simultaneously assigned to an image. Then according to this prior knowledge, we put a cannot link between them. And in the model, we want to, if two labels have a masked link, we want to encourage them to be simultaneously assigned to the image. If they have a cannot link, we want to discourage them to be simultaneously assigned to the image. And under the conditional DPP model, how can we manipulate this DPP to achieve this goal? Basically, how to incorporate this cannot and masked links into the model. Here is, let's get back to the geometry perspective. Remember that the DPP is proportional to the determinant of the submatrix indexed by the elements in a subset. And this determinant of this submatrix is basically the volume of the parallelepiped of the parallelepiped formed by the vectors in this subset. And also note that for two items, if they are similar to each other, which means that the inner product between them is larger, then the volume is going to decrease, and the DPP probability is going to decrease. On the other hand, if the two items are more different from each other, which means that they have a smaller inner product, then the volume of the parallelepiped is going to increase, and the probability is going to increase. This is the geometric property of DPP. So this basically gives us the room regarding how to incorporate this cannot and masked links. So if we want to discourage the co-selection of two items, say label I and J, we basically want to decrease this probability, because the selection is carried by the probability. The larger the probability is, the more likely that the labels are going to be selected. So if we want to discourage selection, we want to reduce this probability. And how to reduce that? We make the similarity of these two items, two labels, to be larger. And on the other hand, if we want to encourage the co-selection of two labels, we basically want to encourage their probability to increase. And to achieve that, we make these two vectors dissimilar. And based on this intuition, we can add the regularization terms over the original objective to incorporate this knowledge. To summarize, for two labels, if they have a cannot link, we increase their kernel value, their similarity, to decrease the probability. And on the other hand, if they have a masked link, we make them more dissimilar to encourage co-selection. There was a question, axis in the volume of the parallelepiped. Oh, so in this case, we have three labels, each have a vector, and the volume is determined by all three vectors. Here for illustration, I just fix one of the vector and consider the relationship between the other two vectors to illustrate the concept of how DPP encourages diversity. But the volume is determined by all the vectors here. Here I'm just doing a controlled illustration. Okay, this is conditional DPP. So far, recall that we have the distribution over subsets, and the subsets can be any subset. It can has 1 element or 10 element. That doesn't matter. But in many applications, we do want to fix the size of the subset. Like in feature selection, right? We have a certain budget, and we only want to select 10 features. Or in document summarization, we only want to select 5 sentences. So how can we define distribution over the subsets where the cardinality is fixed to a particular number k? And this is achieved by KDPP. The difference between KDPP and the vanilla DPP is that here we basically fix the cardinality over the subsets. And the distribution is very easy, right? We just pick up all the subsets which have cardinality of k and calculate this quantity determinant of this submatrix for all these subsets. And the normalizer now would be the summation over all these determinants, right? This is a very trivial definition of KDPP. But in practice, we cannot use this definition to do the calculation because here we still have a huge number of subsets that all have cardinality of k, right? If you calculate this partition function using the brute force manner, that would be hugely expensive. So in the actual operation, we do not use this probability definition, but use some other methods. Now let's discuss one particular thing about KDPP. How can we draw samples from KDPP? The sampling procedure is similar to the one designed for the regular DPP. So we first do Eigen decomposition of the kernel matrix or gram matrix and get all the eigenvectors and the eigenvalues. Then after we get the eigenvalues, we calculate a quantity given in this equation. The quantity is defined in the following way. We take all the subsets where the cardinality is k, and for each such subset, we multiply all the element, multiply the eigenvalues indexed by all the elements in this subset. And we sum this product of eigenvalues over all these subsets and get this definition of EK over all the eigenvalues. And this quantity is going to be utilized during the sampling. The sampling procedure is, there are again 2 parts. In the first part, we select a subset according to this selection rule. So if the uniform, so for item n, we calculate this quantity here using this definition and the eigenvalue. Then we draw a uniform scalar, and if the uniform value is less than this quantity, then we select this element into this J. And repeat this procedure, and we get a subset of items. Then we move to the second part, which is exactly the same as the sampling method for the regular DPP. The only difference is how do you select the first subset. And for the proof of this sampling algorithm, you can refer to the tutorial given by Ben Tasker, which I put it as a reference. Let's see, we have about 10 minutes. Okay. So for this DPP, we are still talking about discrete the distributions over the discrete sets, right? Given n items, we take a subset which has k items, then define a probability over the k items, which is discrete. In other applications, the items are actually continuous. For instance, let's say we have a topic model, say latent Dirichlet allocation. For each topic, we have a topic vector, right, which is a continuous vector. And in the model, we set k topics. So we have k vectors, but each of these vectors have infinitely many different configurations. So essentially, this is still a KDPP problem because from the universal space of Euclidean universal space of the Euclidean space, we want to select k vectors to parameterize the k topics. The difference is for each vector, you have infinitely many different choices that are continuous. So that comes to the continuous DPP, which defines a distribution over k vectors, and each of these vectors has infinitely many continuous choices. And how this distribution is defined, very similar to the discrete case. Let's say we have k vectors. We still calculate the gram matrix or kernel matrix between the k vectors that give us this LA matrix. We calculate the determinant. Then on the denominator, we have this quantity here. EK is what we just defined in this equation. And lambda 1 to infinity are the eigenvalues of the operators. And in the space of continuous space, the eigenvalues are infinite, and they are calculated over something called an operator. So this is the distribution over the continuous DPP, and all you need to remember is that you have k continuous vectors in this matrix A, and this is the probability over the k continuous vectors. For this partition function, in theory, it exists. So that ensures this probability still is valid, but you cannot calculate this quantity here explicitly. And based on this definition, we can still draw samples without utilizing this quantity. And one major application is we want to encourage the k vectors to be diverse. For instance, in topic models, we want to learn diverse topics instead of redundant topics, right? And to achieve that, we basically want to put this prior over the k topic vectors to encourage them to be diverse. I'm going to skip these things and talk about how KDPP is utilized to promote diversity in the continuous case. In the frequentist learning paradigm, we can use DPP, continuous KDPP as a regularizer to encourage the topic vectors to be diverse, right? In the LDA model, we have k vectors. You just put this, you calculate the gram matrix or kernel matrix between the k vectors, then put the determinant of this matrix as a regularization term over the LDA objective function, optimize them jointly to encourage diversity. And in the Bayesian learning paradigm, if you say, I want to learn a distribution over the k topic vectors, in that case, you want to put a prior that encourages diversity over these k vectors. Again, you can use the continuous DPP as a prior to encourage diversity. In the next 5 minutes, I'm going to very briefly talk about some works that are relevant to DPP and how to address the limitations of DPP. So if we want to use the continuous KDPP as a prior to encourage diversity in Bayesian latent space models, what would be the drawback? The first thing is it's not amenable for variational inference. Variational inference, as you learned, is a major type of posterior inference method. Typically, it is more efficient in terms of computation than the MC sampling. Let's say if you use this DPP prior to encourage diversity, you can see that there is a determinant over the matrix. When you are calculating the expectations in variational inference with respect to this determinant, that would be really hard. So DPP is not easy for variational inference, but you can certainly do MC sampling. The drawback is it's going to be slower. Another thing is it cannot be applied to the Bayesian non-parametric models. So in Bayesian non-parametric models, I believe you are going to learn in the next week. We have infinitely many weight vectors. Like in topic models, we have infinitely many different topic vectors. And we still want to encourage these vectors to be diverse. But we cannot use DPP to do that because here it is assumed that the cardinality of this matrix is finite. You cannot calculate a matrix over infinitely many vectors, right? Otherwise, this matrix would be infinite, and how can we take a determinant over an infinite matrix? So this would be some drawbacks of KDPP. So several years ago, we did some work to address these two problems and define a mutual angular process that can address these two drawbacks. The proposed mutual angular process is amenable for variational inference and can be easily extended to the Bayesian non-parametrics paradigm. If you are interested, I put a reference there and you can take a look. I guess that's it. So in the next 2 minutes, do we have any questions? We can discuss. Thanks.